Okay, so this is about calculating moments of inertia. And there's an example in the book, but I'm just going to go through that because it's just as good as an example as any. And it's finding the moment of inertia for a hollow cylinder. So it means that you've got a bigger hole here in the middle, and it's big enough you need to worry about. You can't just neglect that. I mean, most of the inertia comes from the outer parts, but there's still some inner stuff that if you have a hole in the middle. So what we're going to do is we're going to break this up into a situation like this. So remember, the moment of inertia is equal to the summation of m, the mass, times the radius squared. So actually, yeah, that's right. And so what we're going to do is we're going to look at this particular little ring of mass that's at some radius r. And we're going to go between the inside radius to the outside radius. So those are our limits of integration. So this is r outside, this is r inside. So if we look at this infinitesimally wide radial part, it's going to have an amount of mass dm. And what we can do is if you look at just algebra-based physics, what you have is that the moment of inertia at a particular increment out here is going to be equal to the mass of the element. And so we're going to have m, this little, what we call a dm, a differential mass, times the radius squared, the given radius at that point. But the mass of an object is equal to its density times its volume, which is equal to, in this case, its density times the area, which is this little annular area, times the height, because this disk has some thickness as well, which we call h. So this disk has a certain thickness to it. Now the area of this piece, and it's really a differential area, so the differential mass, the density is constant. Let's just put that in there. So you're going to have density times area times height. And the density of the material is constant, and the height's constant, so you can take those outside of the differential. So we get just dA. So what is this little dA equal to? Well, all you have is you can think of it as the circumference times the thickness, which is dr. So that's probably sounds like a good idea. So let's go dH times 2 pi r, which is the circumference, times the incremental radius. We go from here to here, the little step of radius. Now we can assume r is constant for this particular, what we're going to do is basically take the circumference at the average value. But when dm goes to 0, it's basically r. Okay, so instead of using a summation sign, we use the integral of. So we have our mass, which is actually going to be this differential mass. So we have 2 pi r rho h times dr, and then we have the radius squared. Okay, and we integrate from r sub I to the inside radius to the outside radius. So this is a definite integral. Now r is the variable. This is the thing we're going to be integrating, but the other things stay constant. 2 is a constant, pi is a constant, density is a constant, the height of the thickness of the disk is a constant. So we just end up with r cubed dr. Because we have r squared here, we have r there, and we get dr. Okay, so that's just a polynomial. So the integral, the moment of inertia is 2 pi rho h, and we get r to the 4th over 4, and we evaluate that from r sub I to r sub O. Okay, so the moment of inertia is 2 pi, the density of the material times the thickness of the disk, and then we have r0 to the 4th over 4 minus r sub I to the 4th over 4. But if we look at the actual mass of the object, the total mass of the object is going to be equal to the density times the height times the cross-sectional area. Okay, so the cross-sectional area here for the total thing, you've got r sub I here and you've got r sub O out here. Okay, so the area for this whole thing, not just for this differential thing, is going to be equal to, so the area of a circle is pi r squared, so you get pi and you get r sub O squared minus r sub I squared. So we find the area for the outside circle, which is pi r sub outside squared, and we subtract the area for the inside. Okay, so what we should be able to show here is if I factor out the 4, so I'll get 2 over 4 pi rho h, and what I will have is I have this term, so I should be able to factor what I have is r sub O to the 4th minus r sub I to the 4th. Okay, so I've got that squared there. So if you factor this thing, so let's simplify that. So you get 1/2 pi rho h. You'd have r sub O squared plus r sub I squared, and then you'd have r sub O squared minus r sub I squared. So we're just using factoring. This is like x to the 4th minus y to the 4th. What will happen is this times that gives you that. The signs change, so the inner and the outer cancel out, and then you get r sub I squared times negative r sub I squared, and you get that. Well, this thing is pi. If we go back here to the mass is going to be rho h times pi times r sub I squared minus r sub out squared. So if you can see we've got rho, we got h, we got pi, and we got this thing. So let me just mark them off. This, and that is the volume. Actually, is the mass. Okay, the mass. This is the volume times density is the mass. So what we'll get is 1/2 m times r sub out squared plus r sub in squared. And that's the answer that's in the book. And what they say, it says, as a note, check for the solid cylinder r sub I is equal to 0, and so this part drops out, and you get just this less over, which is 1/2 mr squared. Now, so the interesting thing is, why is it plus instead of minus? Well, it's because if you take the mass of the object and you move it further out, which you'd have to do, which would make r sub I bigger, and so by putting the hole in the middle for a given mass, you're going to have a much higher moment of inertia. So that's why they end up adding the numbers together instead of subtracting them. So that's pretty cool. Because you might think the moment of inertia is 1/2 mr outside squared minus r inside squared. But it doesn't work that way. It works that way with you talking about the mass of the object. And you see we did that here. We had r outside squared minus r inside squared, which is the difference in the areas. But when it comes to moments of inertia, you actually add the inside radius squared plus the outside radius squared to get the total moment of inertia. And the other thing too is if these were equal to each other, you'd have a ring, and so you'd have 2 of those, and that 2 would cancel out with that half, and you'd have mr squared, which is the equation for a hoop. Okay, so that's that, and so let's kind of review what I just did there, because I did this kind of on the fly. So what we did is we had a hollow disk. So this was empty, so you could stick something in there, and then it was solid all the way out to here of constant density. The thickness of the disk was h. Our inside radius to the inside of the disk was r sub I. The outside radius is the distance from the center to the outside of the disk. We took this annular ring, which was at some distance r. So this is our differential volume. And what we said was that the moment of inertia for this little ring is going to be the radius of the ring times the differential mass of the ring. Now the mass of something is the density times the volume, and the volume is the area times the height. So what we did is we said the density and the height are constant for the disk, so we ended up with this differential area dA. And the area of this little ring is just going to be equal to the circumference, which is 2 pi r, times the thickness, which is dr. It's kind of like you take this ring and you cut it here and then just stretch it out. So that rho h times dA is the differential mass of the differential mass. So this is dm, this is the radius of the ring, and then you integrate that from the inside radius to the outside radius of the disk. 2 pi rho h, these are all constants for the material. So what we're left with is r times r squared, which is r cubed. You integrate that like this. So we add 1 to the exponent divided by the new exponent. Evaluated at the upper limit, subtracted, evaluated at the lower limit. Then what I did was I rewrote part of it back in terms of the total mass of the disk. And the total mass of the disk is going to be density of the disk, material of the density of the disk, times the volume of the disk. And the volume is the height times the area, which is this area here, not the inner because that's empty. So the area of the outside is pi r outside squared, and the area of the inside is pi inside squared. So you subtract the big area circle here from the, you subtract the little circle from the big circle, and that gives you the net circle there. So that was the mass. So I went to my equation here, which is my one for moment of inertia. I factored out the 4 so that I had r outside to the 4th minus r inside to the 4th. But you could factor that as such. This term times this term times this term times that term is the mass. So we get 1/2 the mass times what's left over, the second factor, and that's the result, which is exactly what the book did. Okay, so that's encouraging.